So guys, we'll begin in just 2 minutes. I forgot to get your probably less than that because I have your thing now. Okay. Alright, welcome everyone to Lab 4. This time around, by the way, I'm just going to tell you guys up front that I've decided not to turn on my my chat and anything because it always causes problems. Let's just keep things simple here. So I'm going to call out your names again. I'm just going to read it out and I'll just look at you guys at the end to see who's here, who's not. And please answer the breakout questions as you did last time. It worked out. Alright, Jotham Abraham, Muhammad Ali, Sanya Anil, Huang Bui, Zayama Inam, Zahao Fang, Yanling Liang, Anjali Mahadio, Arghavan Majidi, Jia Mi, Jordan Morin, Zeno Patel, Alia Pathan, Jetsin Sarvisvaran, Asmi Shukla, Parsansha Singh. So I apologize, usually I do get better at names, it's just that we haven't been able to interact, so I haven't been able to get much better, but hopefully it's coming up from here on forward. So let's begin our lab, and hopefully it's going to be a quick one because we can't really interact. Also, sorry about my, like, too early in the morning. Also, here's my email address. Please write it down if you have any questions. A lot of you guys have been very good with that, so it seems to be working out pretty good. Learning goals of this lab. The learning goals are to understand the applications of simple distillation in identifying and purifying unknown liquids. Sorry, I have a frog in my throat. Number 2, to understand the application of fractional distillation in exactly the same thing, and to calculate the percent composition of both of them. And of course, to learn about azeotrophs. Alright, what is distillation? Distillation is the process of refining a liquid through boiling and condensing the liquids, or the vapors, back into pure liquids. So it's used to identify or purify organic compounds. So it can do both, identify and purify organic compounds. So if you have a mixture of unknowns, you can always purify it, and you can always separate them and identify it. But if you have a pure unknown, you can also use distillation to find out what it is. And we'll talk more about it over the course of the demo, I guess. This interactionless demo. Alright, distillation is a primary method used in the purification of alcohol from fermented plants and fruits. So it's used in a lot of different things, from perfume to gasoline, diesel, lubrication, used in alcoholic drinks, right? So used in a lot of different things. Here is a picture of a very cool distillation apparatus for simple distillation, right? So the purpose of this is to let you guys know it's very important in practical applications, as is the rest of chemistry, right? How does it work? Well, there are a couple of things about this, right? So we're gonna have videos on this, so it's easier for you guys to see than the picture here. So what happens is we have a okay, let's start at start here with the condenser. The condenser is going to be cold, and whatever boils up from your, then I guess we start round bottom flask. So okay, here's the round bottom flask with your liquid in it, which gets placed on top of a heat source. The heat heats the solution. The solution rises up and hits the thermometer. The thermometer is very important, and the thermometer is located below the neck of the distillation neck. I forgot what this part's called here, but that portion there, right? And the reason for that is because you want to calculate the, if you raise it too high, you're going to end up with vapor squeezing through and getting condensed before you actually record its temperature. So it's below the neck of the condenser so that you can record the proper temperature, right? So anyway, so the vapor rises, hits the thermometer, cools down, and moves into this area here. As it cools down, it goes from being gas to liquid, and then the liquid drips downwards, and here we have the condenser. The condenser is much colder than the rest of this. The rest of this will be pretty warm. Room temperature is like the coldest it's going to be. But the condenser will actually have condensate on it. It'll be, when you touch it, cold to the touch. Right? And how we do this is that we fill it with water from the bottom to the top. Right? And we do it in particular from the bottom to the top. The reason for this is because you want to fill up the entire condenser. Right? If you do it the other way, as you have a hole in the bottom, think of it as like a hole in the bucket on the bottom, how can you fill up the entire condenser? You can't. It'll just leak out as you fill it, right? You'd have to fill it way faster than it leaks out, which is hard. But you can do it the other way. If the hole is on the top, then the entire bucket will fill, and then when it gets to the hole, it'll start pouring out. Right? And that's what we want here. Right? So, and then that keeps the condenser nice and cold. We have cold water running through it. Right? And then we have the adapter. So the cold water definitely keeps everything in here cool. Any vapor that comes in here will definitely condense because you're heating it like 70 degrees, and this is going to be at like 5 degrees or something like that, right? Centigrade. So it's going to be much colder than the vapor temperature, and it's going to be much lower than the boiling point. So you're going to end up condensing all of the vapor back into liquid. It's going to drip to the adapter and then get collected in your flask, your receiving flask. Alright, so very simple approach, but here's an important point, that this clamp here that connects to your round bottom flask, the round bottom flask to the adapter, the distillation head, that is extremely important. And the reason for that is because if it doesn't clamp these two in tightly, you could have like some space in between, and the gas will escape and you'll lose everything. It's horrible. Right? Now, let's watch some videos. There's no sound, so don't worry about the sound, guys. So here you can see the simple distillation setup, clamps, elastics. So the purpose of elastics, by the way, is just to keep these things together. If you don't have elastics, they might tend to kind of move out a little bit. It just keeps a little tiny bit of pressure to keep them together. Like little tiny baby amount. Thermometer, notice below the distillation neck. Cold water, yep, receiving is in cold water so that you get nice, so you get a nice condensate, you don't get anything mixing. You turn on the cold water faucet before you start heating. Water in at the bottom, water out on top. Nice and tight. Nice and tight. No holes whatsoever. Right, nice bubbling. You can see the condensate, right? You can see it on the actual thermometer head. It goes down, starts to condense in here, and drips into your receiving flask. Right? So that's how simple distillation generally works. There's also a second video about unknowns. Sorry, I'm going to restart that for you guys. So you have an unknown liquid of 25 ml. You're going to put it in your round bottom flask. So this is what you guys would be doing in the lab. This is actually a pretty chill experiment. I've done this one like 3 or 4 times. It's the easiest one because you just set stuff up and you just wait for it to boil while recording temperatures every like 2 minutes. Right? So a lot of fun. In person, not on video. Right? Oh, make sure to add boiling chips. Very important because you want to get a nice boil. You don't want anything superheating in there. Remember, you also don't want anything to be more than 2/3 full. You don't want the round bottom flask to be more than 2/3 full or less than 1/3. Right? Not too much full because then you'll get too much bubbling, too much air, too much pressure, and not too little because you might end up with peroxides or some things that could become superheated and explode. Yep, to set everything up. This is the heating thing, by the way. So heat turned on. You can see it start to boil. It's going up, going down. And then you can use the melting point. Wow, you can use the boiling point to tell you what compound it is. Right? And you can use a graduated cylinder instead of a flask in order to record like how much volume per period of time. And then you can graph that, and I'll show you guys an example of a graph later on. Right? So that's that. Alright, so that was simple distillation. What about fractional distillation? So now you're wondering, wait, fractional distillation, that sounds very similar, but, still different. What is it? So you do fractional distillation when you have a mixture. You do simple distillation when you have a pure unknown or pure compound, right? So if I gave you something that said, I know this is 100% pure, I don't know what it is, but it's 100% pure, whatever it is, right? Then you would do simple distillation. But if I told you, here's a mixture of stuff, I mined it from, you know, below, it's like diesel and whatever else, oil and who knows what else, do something, separate, you know, the octane from this, right? And I gave it to you, and it's left it with you. You'd have to do fractional distillation, right? So in our example, on the slide, not the cool example I gave you about diesel and octane, the fractional distillation consists of methanol and water. So notice something right here. They both have different boiling points. And that is going to be a very important fact for us, right? Because what we can do then is that we can heat the methanol up at 70 degrees Celsius, about 65 even, right, to remove the methanol from the mixture, but the water is still there because it takes 100 degrees. So it's too cold for water, but hot enough for methanol. That way we can separate one instead of the other, right? And each of the fractions will be collected like within the amount, and you'll be able to see it. Like you can see it on the graph, you get jumps, right? So for example, the volume per temperature is going to be near about constant, and all of a sudden it's going to rise, and then whenever you're done with your methanol, like let's say you're heating at 70 degrees, right? So before you get to 70, you're gonna have no volume, maybe like a drop or something like that, right? As you get to 65, you'll start getting a drop, 2 drops, something like this. Then when you get to around 66, 67 or something, I mean, if you're really good, you'll get it at 65. Now, if you're really, really good, you'll get it at 65, right? It starts to rise. The volume, it starts dripping a lot. Like the volume increases, but the temperature stays the same. So your graph on the bottom, temperature on bottom, volume on the x-axis, temperature on the x-axis, volume on the y-axis is what I meant to say, right? So volume would stay the same for the longest time while temperature increases. Once temperature increases at 65, you'll see a sharp increase. The volume will increase, but the temperature will stay the same. And then it'll stay there for as long as you have compound. So let's say you have 25 milliliters of methanol and 25 milliliters and 50 milliliters of water, right? So the volume will increase to 25 mils because all the methanol is dripping off. Then it's going to stop because you're out of methanol. Then the temperature is going to increase and the volume will stay the same until you hit 100 degrees. Then it'll rise again because now you're boiling off the water, right? So you'll see 2 plateaus, right? Very cool, right? Simple distillation is going to be a little bit hard for that because too many plateaus, too many things. So what we do instead is that we use something called a fractionating column, and we'll see that in the next slide, right? And there's something very important theory-wise for you guys, right? It's called the theoretical plate. The theoretical plate is basically the vapor front, right? It's the region on the fractional column in which the liquid and vapor phase of a component are at equilibrium. You can see it, right? And I'll show it to you in the video. It'll be much more clear in the video. Alright, before we go on to fractional stuff, let's talk about distillation of mixtures and liquids. So this here is our composition graph, boiling point temperature composition graph. On the left hand side we have 100% A, on the right hand side we have 100% of B, right? In between we have different stuff. So a note about these lines. The 50-50 mark is this line, the second line is A, the third line is B, right? So that's the lines coming from the x-axis. Never mind this tiny dot here, right? Now what do we see in this graph? At the bottom, X to W to Z, what we see is the boiling point, right? It's the boiling composition, like it's the boiling point of the solution mixture. I hope that's clear, right? I mean, usually I have you guys face to face, so but anyway, so it's the composition at the boiling point. So let's say at A you have 80 degrees, you have 50% A, 50% B, right? Something like that, right? And X to Y to Z, so the top line, right, is the vapor composition, right? So the vapor composition is not necessarily the same as the boiling point of a solution mixture, right? Because even if you have a composition of 50-50 of A and B, but B boils more than A, so you're going to obviously have more B in the air than A, right? So even if there's a 50-50 of, and let's take the 50-50 line here at W, right? So at W is at 50% A, 50% B composition. So you took 25 mils methanol, 25 mils water, and you mixed it together. But we know that at 80 degrees, there's a lot more methanol in the air than we have water, right? So what's going to happen is that your vapor composition at that temperature is going to be, at W, is going to be Y. Does that make any sense? And I don't know if you guys understand, write this down and email me, right? So I'm going to go over it again one more time. So if you have a composition of methanol which boils at 64 degrees, 65 degrees Celsius, and you have a mixture, an equal amount of water which boils at 100 degrees Celsius, and you're only heating at 80 degrees Celsius, right? Even though the mixture is 50%, 50-50, the liquid in your round bottom flask is 50% methanol, 50% water, the vapor that's coming off is going to be mostly methanol, because the water isn't going to boil at 80 degrees. It's going to boil at 100 degrees. So you have very, very little of water, and you have much more methanol. So that's what you see in this graph, is that even though you have a 50-50 composition, you have much higher concentration or composition of B than A. Right? And to find it, let the composition of B to A, so you draw your line, you'd go to the right, you'd find the point of A, then you drop it down and you'd find A. Right? And then now you'd know, aha, this is the composition in the vapor. Right? And then similarly, if you had A, at this point you could do B, right? So if you condense and reheat it at 75, at this point, right, you just draw the line here to B and you drop it and you see it. So basically, as you go lower and lower and lower, the vapor point composition is going to become whatever it is B is. But as you go higher and higher and higher, you're going to get more and more of A. Right? And that makes sense. And you're going to get both of them actually if you go higher and higher and higher. Right? And the reason for that is because a lot of your stuff, both of them are boiling at this point. But here, mainly only one of them is boiling. Right? So I hope that makes sense. And if you were to do this stepwise, so what this talks about repeated vaporization means that if you were to boil at 80 degrees Celsius, the composition you'd get, and you boil it all off till it stops boiling, your composition at the end would be A. Right? Then if you took that A, like when you put it into your collection flask, you have A. Then you toss out the old stuff in your round bottom flask, and you take what you collected, put it back in your round bottom flask, right? And then heat it again, but this time at 75, right? What you're going to end up with is B. And you keep going from B to C to D to E to F to whatever, and then finally when you get to this point here, you have only 100% B. As you can see, very tedious and annoying, right? So if you have a mixture of composition, simple distillation, not the way to approach it. What is the way? Fractional distillation. This is a fractionating column right here. So it looks like this, got a bunch of metal filings around it. You're going to wrap it with aluminum foil to keep it insulated, and you'll be able to see the vapor front on it. Right? What it does is that you add it. So it goes like there's your round bottom flask, then the fractionating column, then you have your thermometer on top. And the point of this column is just to give you extra space so that your stuff can, things can boil at different temperatures, and you can control that, and you can change the vapor front. Right? And never ever distill to dryness, of course. Right? And with this fractionated column, you can have compounds that have a boiling point difference of greater than 20 degrees separated, that can be separated. Right? But remember, they can't be too close, otherwise you can't really separate them. You can't get too many vapor fronts. It's too difficult. Right? So, and again, one more time, the theoretical plate is the region along the fractionating column where the vapor and liquid are at equilibrium. Right? Video time. So here's the setup. So if you remember from last time, we just put the distillation head on the round bottom, but now there's this fractionating column in between, right? So round bottom, fractionating column, and everything else is the same. We just lifted up our collection flask with a jack. That's all that happened. Right, retort stands, of course, got to keep everything stable. Clamps, very important. Got to keep everything supported. Hot plates, mantle, jack. Elastics, same thing. Everything's the same except for the fractionating column, right? And of course you have a mixture in your RBF. So we've started to heat it. It's starting to rise. The fractionating column, stainless steel column packing, so that so that basically what it does is that it keeps anything that wants to condense, it keeps it condensed. So you only get the vapor, and so you have a much better separation. Right, notice the bulb is below the condensation head so that you can record the temperature. Same water in, water out method. Water in from the bottom, water out from the top. Turn on the cold water. Well, you always want to turn on the cold water before you start heating because you want it to be cold by the time you start heating. Otherwise, if it's still hot, you're not going to do much separation. Okay, here we go. So they've insulated it. They're using aluminum foil to keep it nice and warm. They're also insulating the fractionating column. And they're insulating the other part too. But you want to keep the thermometer available, otherwise you can't record the temperature. Right, and there you go. You start to see drops of condensate. Same approach exactly. It's not even very different. We're done the video. Oh yeah, sorry, we're done the video. Yeah, and then you just collect it. Right? So, very straightforward. So let's see what this guy's doing from the beginning. This is an unknown mixture, right? You put it into your RBF, round bottom flask. Boiling chips, very important. You don't put like a scoop full of boiling chips ever, you put like 2. And you measure the volume in the graduated cylinder. And I think that's it. Yeah, there we go. Right, pretty straightforward, pretty awesome, pretty easy. So that's what it looks like, and you saw a much better picture in your video right there. Alright, so this is a really nice summary. Yes, summary. Right? Simple distillation is for single distillation. Right? Fractional is for multiple. Simple does not use a fractional column or fractionating column. The fractional does. Right? Simple identifies pure organic mixtures. Right? Pure organic solvents, we should say. It's not. How can it be? I guess you could also purify it, but it's too difficult. And it's only effective for things that have large differences in boiling point, whereas fractional can do much more than that. Alright, what is the purpose of today's experiment? Today's experiment is to carry out part 1, to carry out a simple distillation. Part 2, to carry out a fractional distillation. Hooray! It's actually a really cool lab. When you guys get a chance, feel free to watch the lab skills video. I've been told you guys have already seen it, so you guys should already be well aware. Alright, so one thing that's going to come up is, what is an azeotrope? So an azeotrope is a mixture that distills at a constant temperature without change in composition. What that also means is that on the boiling point graph, there's no change. And hold on, I have a graph afterwards. On the boiling point graph, there is no difference in the composition it's boiling at and the vapor composition. Right, so you get the same composition boiled off as you get in the mixture. Right, that is an azeotrope. So an example azeotrope, and then I'm going to talk about the slide in a moment. Just going to show you guys what it is. I'm going to talk about what I want to talk about, and then I'm going to go over the slide. Alright, so for example, if you have a 95% mixture of ethanol and water, right, and you boil it, because it's an azeotrope, what's going to happen in the vapor is it's going to also be 95% ethanol, 5% water. You're just always going to get that. You're not going to get any more pure than that, right? Now here is the boiling point graph of water and ethanol mixture. So here we have 100% ethanol on the left hand side, 100% water on the right hand side. We have our boiling points here. Notice the dip here, the minima, I guess, right? And we also have the vapor composition point, right? Vapor composition point temperatures here on the side, on the top, right? You'll notice a very important point here at 95%. Right, at 95%, you draw the line down here. You end up with the composition, the vapor composition is equal to the composition of the liquid on the bottom of your starting solution. Right, that is an azeotrope. All right, so let's talk about this water ethanol mixture from beginning to end. So now I'm talking about what's written on the slide. Right, so let's start with a 25% ethanol, 75% water mixture. If you were to heat this mixture, you would get all the way up to point A. The vapor composition would be B. Right, and then you'd cool down the vapor, condense it, collect it in your graduated cylinder. Then once it's all collected, you'd throw out whatever's in your round bottom flask, and you'd put B back in there, and then you'd keep going. And B is about 50-50. Now, even though at temperature A, you're gonna get like even if you start with 25% ethanol, 25% ethanol, 75% water, you're gonna end up with roughly 50-50 in your graduated cylinder, right? Because the vapor composition is gonna be around 50-50, right? Then anyway, so you take your whatever's in your graduated cylinder, you put it into your round bottom flask, and you heat it again at temperature C. Right? So you heat it, it goes, then you have D. And then you continue this procedure, then all of a sudden you're going to start to find your composition and vapor composition don't change anymore. You're not going to get any purer than that. Now, you're not going to get any more than 95%. And that is the azeotrope. That's an azeotropic solution. Right? And that's what happens. So how do you, if you know you have an azeotrope, how do you calculate it? Well, you might also ask, if you know it's a simple distillation, how do you calculate it? Here's how you calculate it. So, the percent composition, so by the way, you guys are starting with only 25 mils. That's why the volume is divided by 25 mils. So, if you have a simple composition, right, whatever you get, you just, if you look at our graph here, you look for the point with the sharpest change, so right here, right there, sharp change. Right? So you put that point, you find the volume, there should have been a line. There it is. Wow, weird. There it is. Okay, now it's working. Sorry. So now you have a line, so 20 mils. So at 20 mils you get this, right? So this is what our graph tells us, that's how much volume we have. So we plug it into our calculation. Percent composition is equal to 20 over 25, right? Because 25 mils was the total volume we put in. 20 mils before it starts to collect a lot. Right? Times 100%, you end up with 80% composition. Great. But what happens if this was an azeotrope? Right? If it's a simple compound or a non-azeotrope, this calculation works perfect. What happens if it's a 95% ethanol, 5% water mixture? Well, the calculation is exactly the same, except you know that 95% of whatever it is you collect, only 95% is ethanol. Right? If it was not an azeotrope, it was 100%, then you just get 80%. But because you know that the 20 mils is not all ethanol, some of it's going to be water. In fact, 95% of that 20 mils is going to be ethanol, and 5% of that 20 mils is going to be water. So to get the amount of ethanol, you multiply it by 95, and you get 76% composition. I hope that's clear. If not, shoot me an email, and we'll talk about it. Right? And basically, again, going over the azeotrope composition, you just multiply the percent composition by the azeotropic percentage. That's all you do. Right? So in our case of ethanol, 95% ethanol, that would be, you could also get the same number by doing putting the 95% at the end and just having the 80 times 0.95, right? And the reason for that again is because although you collected 20 mils, you know, because it's an azeotrope, that 5% of that 20 mils is water and 95% of that 20 mils is ethanol. So that's how it is. Awesome. Safety. Add boiling tips. Keep flammable solvents away. Handle in fume hoods. Do not distill to dryness, as peroxides and stuff will explode. MSDS. I'm sure you guys already did this. Alright, procedure 1. The link to the full experiment, by the way, doesn't really work. It's not really a thing. Feel free to go and visit it on your own time if you want. Anyway, so what happens is you set everything up, you get your 25 mils for the simple distillation. You set everything up, you get your 25 mils of unknown compound, whatever it may be, right? A, B, C, or D. You add your boiling chips, you put it in, you get my approval, you start boiling, then you start collecting distillate at about 1 mil per 1.5 to 2 minutes, right? And that's how you do it, right? You record in your lab notebook the temperature for each 1 mil collected, and you graph it later on, right? When you're finished, you turn everything off, clean everything up. It's not even hard. It's just like the easiest lab you're ever going to do. Basically, if you want to put it into like terms any person can understand, you basically set up your apparatus, put in your 25 mils of distillate, heat it, collect it in your thing, in your graduated cylinder, and you just mark down how much is dripping off every minute and what the temperature is, right? Minute or 2 minutes, right? And the temperature. Very straightforward, very easy. Couple of things for you guys to note. As we mentioned before, water should go in from the bottom, out from the top, so that it fills up and keeps the condensate cool. Sorry, water in the condenser should go in from the bottom, out from the top. Sorry, I forgot the condenser part. Right, so water from the condenser should go in from the bottom, out from the top, so that it fills the whole thing up and keeps it all nice and cold. How to obtain, observe, and keep reaction at equilibrium. You just keep temperature same, and you can add aluminum foil around it so that you don't lose heat. Why should distillation be done slowly? It should be done slowly because you want to keep the temperatures the same. If you heat it too fast, you're going to end up with like sputtering and like you're going to get evaporation of both mixtures, even if it's above the heating point, because the temperature change is too drastic for the molecules. Coolio. Next one, fractional distillation. Same exact thing, except you're going to put the fractionating column between the round bottom flask and the thermometer, so the fractionating column goes in between. Same exact thing. Results. You're going to put your results into here. Now, I believe the professor is going to assign a separate sheet with something like that with you guys to get you the data to put in here. But this is what your results are going to look like. You're going to just put in unknown distillate amount, and this is the volume. Right, and this is the volume. Remember, we saw the graph change, right? It starts to rapidly change, so the volume there, right? Boiling point, so the temperature at that point. Same thing with fractional. Then you get the first distillate and second distillate, and you're not supposed to just 97%, 97 degrees, but it'd be water, so 100 degrees approximately. Right? Cool, and that basically completes this experiment. At this point, you are now in a better situation to understand the apparatus setup and technique of simple and fractional distillation. You should be able to explain the application of distillation and identification of purification of liquids. You should now have a better understanding of azeotropes. I certainly hope you do. Alright, breakout group question. Feel free to take a picture. I'll give you guys a minute. Email it to me. Oh, I should have my email on the slide. 1 second. So take a picture of the question. utoronto.ca. It's .utoronto.ca. I'm pretty sure you guys already have it because you guys already said it last time. Alright, breakout groups, and then thank you so much. I'll see you guys in 2 weeks. I'm gonna turn off my camera.